Hello everyone, today we are going to discuss about measurements of sonic attenuation and amplitude. So let's start from the definition of amplitude. Amplitude is the difference between maximum displacement of a wave and the point of no displacement, or the no point. The common symbol for the amplitude is A. Sonic attenuation causes. Attenuation is caused by both absorption and scattering. Absorption is generally caused by the medium. This can be due to energy loss by both viscosity and heat conduction. Attenuation due to absorption is important when the volume of the material is large. Scattering, the second cause of attenuation, is important when the volume is small or in cases of thin ducts and porous materials. Here we can see three graphs which demonstrate us how connected propagation distance with different parameters. First graph demonstrates us propagation distance under different pressure levels. The second one shows us propagation distance under different diameters. And the last one is the propagation distance under different frequency bands. Viscosity and heat conduction. Whenever there is a relative motion between particles in a media, such as in wave propagation, energy conversion occurs. This is due to stress from viscous forces between particles of the medium. The energy lost is converted to heat. Because of this, the intensity of a sound wave decreases more rapidly than the inverse square of distance. Viscosity in gases is dependent upon temperature for the most part. Thus, as you increase the temperature, you increase the viscous forces. This graph demonstrates us how amplitude of the sonic wave depends on distance and time. It can be clearly seen that amplitude of the wave decreases when time and traveled distance grows up. Boundary layer losses. A special type of absorption occurs when a sound wave travels over boundary, such as a fluid flowing over a solid surface. In such a situation, the fluid in immediate contact with the surface must be at rest. Subsequent layers of fluid will have a velocity that increases as the distance from the solid surface increases. The velocity gradient causes an internal stress associated with viscosity that leads to a loss of momentum. This loss of momentum leads to a decrease in amplitude of a wave close to the surface. The region over which the velocity of the fluid decreases from its nominal velocity to that of zero is called the acoustic boundary layer. This picture shows what goes on when the wave goes through the boundary layer and how the direction of propagation changes under these processes. As we can see, angle between normal line and reflected wave and normal line and normal wave is equal. Causes of the attenuation in the borehole. We must distinguish two cases. First one is open hole and second one is cased hole. The principal causes of attenuation in open hole logging are: first one, attenuation in the mud; second, attenuation by transmission of energy; and third one, attenuation in the rock. Attenuation in the mud. The normal drilling muds which contain solid particles, we have to add the effect of dispersion. It is estimated that the total dispersion is of the order of 0.02 decibel per pound for a frequency of 20 kHz. In gas-cut muds, the attenuation caused by dispersion is very large, so making all sonic measurements impossible. Attenuation by transmission of energy across the mud formation boundary for waves arriving at an angle of incidence less than critical. The coefficient of transmission depends on the relative impedance of the rock and the mud. As the impedance of the mud is about constant and there is little variation in rock density, the ratio of impedances is effectively proportional to the speed in the rock. As regards attenuation in the rock, first one, the frequency energy loss. In non-fractured rocks, the attenuation is longitudinal and transverse waves is an exponential function, delta equal E in the power of AL, whereas A the sum of ALs and L is the distance traveled. When the rock contains hydrocarbons, a greater attenuation of longitudinal wave is observed. In the case of gas for oil, the factor A non-zero. From this we can deduce that this viscosity of the fluid has an effect on the attenuation factor. The second one is loss of energy through dispersion and diffraction. In some, this appears mainly in the vaggy rocks. As regards cased hole, the attenuation is affected by the casing, the quality of cement and the mud. If the casing is free and surrounded by mud, it can vibrate freely. In this case, the transfer factor of energy to the formation is low and the signal at the receiver is high. If the casing is inside a cement sheet that is sufficiently regular and thick, 1 inch at least, and the cement is well bonded to the formation, the casing is no longer free to vibrate. The amplitude of the casing vibrations is much smaller than when the casing is free and the transfer factor to the formation is much higher. So, here is measurement of attenuation. Commonly, this is not possible directly, so indirect measurement amplitude used. We call it cement bond tools. Measure the bond between casing and the cement placed in the anodes between the casing and the well bore. The measurement is made by using acoustic sonic and ultrasonic tools. The measurements of industry standard sonic tools are usually displayed on a cement bond log in millivolt units, decibel attenuation, or both. Reduction of the reading in millivolts or an increase in the decibel attenuation is an indication of better quality bonding of the cement behind the casing to the casing wall. Stokes' law of sound attenuation is a formula for the attenuation of sounds in a Newtonian fluid, such as water or air. Due to the fluid's viscosity, it states that the amplitude of a plane wave decreases exponentially with the distance traveled at a rate alpha. Variable density log. A presentation of the acoustic waveform at a receiver of a sonic or ultrasonic measurement in which the amplitude is presented in color or the shades of a gray scale. The variable density log is commonly used as an adjunct to the cement bond log and offers better insights into its interpretation. In most cases, microanomalous and fast formation arrival effects can be identified using this additional display. In open hole, it may be displayed alongside the sonic log, transit time as a qualitative presentation of the acoustic wave train, and is sometimes used for fracture detection by examination of the chevron patterns given by Stoney wave reflections and other wave reflections at fractures crossing the borehole. Here are used references on material which we used to create this presentation. So thank you very much for attention. This material was prepared by Shingiz Khan Alibek, Rayhanov Ali Khan and Mavjud Atkur. Our supervisor is Mr. Nadir Ablay, Kazakh British Technical University.